Today we'd like to go through an example of using power series to get a solution to a second-order linear homogeneous differential equation at an ordinary point, in this case where x equals 0. That means we want the power series centered at 0. We're going to look at the differential equation 1 minus x, that quantity, times y double prime, minus y equals 0. Now, in order to start working, we want to divide through by the 1 minus x, and we'll write that as y double prime minus 1 over 1 minus x times y equals 0. And we'll notice that here, this function 1 over 1 minus x is analytic at 0. We all know the power series for 1 over 1 minus x. I chose it for this example because there's a very simple one. 1 over 1 minus x is just 1 plus x squared plus x cubed, etc. That's the sum of x to the n. And this power series is valid when the absolute value of x is less than 1. In other words, the radius of convergence is 1. Now, because the coefficient functions, in this case, we want to write, when the equation is written as y double prime plus p of x, y prime plus q of x, y equals 0. These coefficient functions p and q are both analytic at 0. P, of course, is just 0. Q is this function 1 over 1 minus x, or minus 1 over 1 minus x, which is analytic at 0. The minimum radius of convergence is 1. Obviously, the 0 function has a radius of convergence which is infinite. But the minimum radius of convergence is 1 for the coefficients. So what our general theory for solving second-order linear homogeneous differential equations using power series tells us that we should get a solution as a power series a solution y of the form a naught times some function y1 of x plus a1 times some other function y2 of x where the functions y1 and y2 are both analytic with radius of convergence 1, or at least 1. Now, how we go about doing that is what we want to see today. We want to have our solution of this form, y is the sum of a sub n x to the n. That would be a naught plus a1x plus a2x squared plus a3x cubed, etc. And the good way to think about this is a naught is just y of 0, of course, and a1 is y prime of 0. The claim is that these should be arbitrary. And then in order to have y satisfy the differential equation, all the other coefficients we should find depend on a naught and a1. In order to find how they depend on a naught and a1, we compute y prime, which is just the sum from n equals 0 to infinity of n a sub n x to the n minus 1, which after getting rid of the 0 term and then re-indexing, we get the sum from n equals 0 to infinity of n plus 1 an plus 1 x to the n. We do the same sort of thing as we've done before to find y double prime is this sum of n plus 2 times n minus n plus 1 times a sub n plus 2 x to the n. This is just going to be 2a2 plus 2 times 3, which is 6. I'll leave it as 2 times 3 here. a3 x plus 3 times 4, a4 x squared, etc. Then our differential equation can be written in the following form. This is y double prime. This is exactly how we computed for y double prime. There's 2 times 3, 3 times 4, 4 times 5, 5 times 6, etc. This is 1 over 1 minus x, and this is our function y. So this is the differential equation. Y double prime is 1 over 1 minus x times y, which is equivalent to y double prime minus 1 over 1 minus x times y equals 0. And then for this product here of power series, we can do a formal power series multiplication. What is the constant term when you multiply these power series? Well, the only way to get a constant term is a naught times 1. That's a naught here. How do we get the coefficient on x? Well, we could have a naught times x, or we could have a1x times 1. So we get a naught x plus a1x. How do we get a coefficient of x squared? We could have a2x squared times 1. We could have a1x times x. We could have a naught times x squared. So we have these three pieces that add together to give us our total x squared term. And the pattern is very similar. To get x cubed, you could have the a3x cubed times 1, the a2x squared times x, the a1x times x squared, or the a naught times x cubed. And that will continue on and on. Then we want to equate coefficients. In order to have y double prime equal this, we need 2a2. So let me write this here. We need, I'm going to write them over here, 2a2 must equal a naught. We need 6a3 equal to a naught plus a1. We need 12a4 equal to a naught plus a1 plus a2. We need 20a5 to equal a naught plus a1 plus a2 plus a3 up there. And taking each one and dividing by the coefficients, we get a naught equals, I'm sorry, a2 is just a naught over 2, a3 is a naught over 6 plus a1 over 6. That's just dividing this here by 6. a4 is a naught plus a1 plus a2, all of this over 12, which is 1/12 a naught. Plus here we have a2 over 12, and a2 is a naught over 2. So this term, the 1/24 a naught, comes from the a2 over 12, and then we have a1 over 12 as well. And we just combine these. The sum of these two terms gives us 1/8 a naught plus 1/12 a1. In other words, we can simplify everything to be some constant times a naught plus some constant times a1 and get rid of all the other a's. a5 similarly is a naught plus a1 plus a2 plus a3 over here, divided by 20. That's a 20th a naught plus a 20th a1 plus a2 over 20, which gives you a 40th a naught, plus a3 over 20, and remember a3 is this, so that a3 over 20 gives you a naught over 120, this part, plus a1 over 120, this part. So when we add those all together and simplify a bit, a5 is just 1/12 a naught plus 7 1/20ths a1. And the point is, even without worrying about getting a nice general formula, though you actually could find something moderately complicated, we don't really care about that now, you could just spit out these coefficients recursively. Trivial computer program would let you do that, and spit out each of these coefficients, each of the a's, in terms of a naught and a1, just by continuing this process. When we do that, we find that our solution function y, which is just a naught plus a1x plus a2x squared, etc., is using the coefficients we found in the past, on the previous page, a naught plus a1x plus, I don't know why that 2 is there, a naught over 2 x squared, that's our a2, plus 1/6 a naught plus 1/6 a1 x cubed, plus an 8th a naught plus a 12th a1 times x to the 4th, and keeps going here. The a sub 5 was 1/12 a naught plus 7 1/20ths a1. That's the coefficient of x5. Now I'm going to take all of this and split it into all the things that have a naughts in them. So here we have a naught times 1. Here we have a naught times a half x squared. Here we have a naught times a 6th x cubed. Here we have a naught times an 8th x to the 4th. Here we have a naught times 1/12 x to the 5th, etc. And all the pieces that have a1. Here's a1 times x. Here's a 1/6 a1 x cubed. That's for this term. The 1/12 a1 x to the 4th, this term times a1. And the 7 1/20ths a1 x to the 5th here. And as I said, we could continue to get more and more and more. We'll call this function y1. By this, I mean the whole thing. We'll call that function y1. That's a function of x. And we'll call this function, this whole thing here, y2 of x. And there we see our general solution y is just a0 times y1 of x plus a1 times y2 of x. Remember here, a0 and a1 are arbitrary real numbers. And again, I'll remind you, if you give me an initial condition at 0, a0 will be exactly your y of 0, and a1 will be exactly your y prime of 0. So you tell me your initial condition, what y of 0 is and what y prime of 0 is. That will tell you right away without having to solve any system of equations. It'll tell you exactly what a0 and a1 are. In other words, you'll be able to solve any initial problem right away using this function as y1 and this function as y2. Now, there's no nice elementary representation for these functions y1 and y2. Just to show you what they look like, I've kind of graphed them here. At least what I've graphed is the fifth degree Taylor polynomials for both. In other words, instead of graphing all of y1, I've just graphed this approximation for y1, which is this fifth degree polynomial. Of course, if you had higher degree terms, we'd get a more accurate version, and you could have a computer compute many, many, many more terms and get a really good idea what shape y1 is. This fifth degree Taylor polynomial for y1, this fifth degree polynomial approximation, will be very, very, very close to what y1 is, at least if you stay very close to x equals 0, so in a neighborhood of the origin. And the more terms you take, the better, the larger an interval will be on which you have a good approximation. Similarly, I've graphed, this red one here is y1 of x, the graph of y1 of x. The black one here is the graph of y2 of x. You see y1 of 0 is 1, and y1 prime of 0 is 0, and the opposite for y2. y2 of 0 is 0, and y2 prime is 1. This now gives you a very good idea what general solutions to this differential equation. I'll remind you the differential equation started out as 1 minus x y double prime minus y equals 0. I believe that was it. So solutions to this differential equation are in general linear combinations of these two. And if I give you as an example the initial value problem with this differential equation with y of 0 equals 3 and y prime of 0 equals minus 1, then our unique solution to that initial value problem is y equals 3 y1 of x minus y2 of x, because we have these coefficients 3 and minus 1, and then you can just compute this exact function with a 3 and minus 1 there, and you'll have your unique solution to the initial value problem.